Hello, and welcome to our presentation about the reinforcement learning task in Robotics Project Work. I'm Casey Jones, and I worked with Tita Kempi and Vaino Bolari. We were given a Simulink model of a hydraulically actuated robot manipulator arm containing 3 joints, 2 rotational and 1 prismatic, which moves in a 2-dimensional plane, and asked to develop a reinforcement learning-based controller to control the robot's end effector position using torque commands, as well as to model its kinematics and dynamics using a Gaussian process for the purpose of informing the reinforcement learning model's reward function. Additionally, we were asked to get co-simulation working between our PyTorch models and the existing Simulink model. We began by extracting data from the Simulink model, generating a series of random trajectories and dumping their states over time to CSV data in order to support the training of our 2 PyTorch models. The training data was fed to the Gaussian process model first in order to train it, and the Gaussian process in turn was used to train the reinforcement learning controller. At each step, the reinforcement learning controller would generate its predicted next torque control values, and the GP model would update its predicted state based on those and the existing state. Here's a more detailed model of our Gaussian process architecture. As stated, it takes the torque command from the reinforcement learning model plus the existing state consisting of joint values, end effector velocities, and accelerations, and outputs the predicted next state, including the end effector location, end effector velocities and accelerations, and the predicted next joint configuration. Here's a quick demo of using our Gaussian process training. We first clone the repository, link up our dataset and trained models folder, and then we begin the training process by specifying the path to our data and the path where we would like to save our model. And we can see it moving along. So next, let's take a look at some testing. That was not our best model since we only trained it for a moment, but here's a more trained model predicting the next end effector location and accelerations. Next, let's take a closer look at our reinforcement learning model. It takes in the existing state and predicts the goal location and predicts the next joint torque command for each joint in order to move the end effector towards the goal location. We can see a quick demo of our reinforcement learning model's training loop. Training on a single goal. It alternates between exploration and exploitation. And we can see that the model is moving slowly closer to its goal, which is usually the case. However, one problem we've experienced is that the model will often overshoot and continue moving past its goal. So we need to do more work in order to determine the cause and solution of this problem. But in this example, it's doing quite well and getting very close to its goal. That's it. Thank you for your attention.